Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into some really fascinating stuff, analyzing, predicting, and even controlling how a reasoning model will think. It's a big topic with a lot of implications.
Yeah, this is the kind of thing that keeps me up at night in a good way. The idea that we can start to dissect the inner workings of these AI systems, especially when we're talking about potentially achieving AGI, is just mind-blowing. It's almost like we're peering into a black box and finally seeing how it ticks.
I'm a little more cautious, I think. Peering into the black box is one thing, understanding what we see is another, and then controlling it. That sounds optimistic, to say the least. I mean, are we sure we're not just seeing patterns that we think we understand?
I agree with the cautionary sentiment there. Analyzing and predicting? Okay, we're making progress. But controlling? That implies a level of understanding that I just don't think we're anywhere near yet. It's like we can see the input and output, maybe even some of the intermediate steps, but we don't really know why it's doing what it's doing at a fundamental level.
That's a fair point. Control is definitely the aspirational end goal, but the first steps are really about understanding. And there's some interesting research coming out that's making inroads. I've been thinking a lot about the gap between current AI and human cognition, and it feels like we're missing some key insights about how biological brains actually do reasoning. It's more than just statistical pattern recognition, right?
Absolutely. But I also think we shouldn't underestimate the power of those statistical patterns, especially with the scale of data and compute we have now. I mean, look at the large language models. They're exhibiting behaviors that, just a few years ago, we would have thought were impossible. Isn't that evidence that we're on the right track, even if it's a brute force approach?
I think that's the trap, though. They appear to be reasoning, but are they really? They can generate text that sounds coherent and even creative, but when you probe them on fundamental logical principles, they often fall apart. It's sophisticated mimicry, not true understanding.
Exactly. It's like they've memorized the script but don't actually understand the play. And that's where I think the whole spatiotemporal aspect comes in. These models are largely atemporal and aspatial. They don't really understand relationships in space and time, which I think is crucial for real reasoning.
So, Donald, can you elaborate on that a bit more? What specifically do you mean by spatiotemporal reasoning, and why is it so important?
Sure, think about how we navigate the world. We're constantly updating our understanding of where things are in relation to each other, how they're moving, and how those relationships change over time. We're translating between different coordinate systems all the time: visual input, motor commands, internal representations of space. Current AI just doesn't do that very well. It's like, imagine trying to teach a robot to assemble a piece of furniture using only text descriptions. It might be able to parse the instructions, but it wouldn't have the intuitive understanding of how the pieces fit together in 3D space.
Okay, I see what you're saying. But couldn't you argue that with enough training data, simulations, videos, robotic manipulation examples, a deep learning model could eventually learn those spatiotemporal relationships implicitly? It might not be doing it the same way a human brain does, but it could achieve the same outcome, right?
But that's the problem with implicit learning. It's not transparent. We don't know how it's learning those relationships, and that makes it difficult to debug, to generalize to new situations, and to trust. And it's incredibly data inefficient. We can learn a new spatial relationship with a few examples, whereas a deep learning model might need thousands or millions.
This brings me back to the biological perspective. The brain is incredibly efficient at learning and reasoning, and it does so with relatively little data. There's something about the architecture and the learning mechanisms that allows it to generalize in a way that current AI struggles with. And I'm particularly interested in how the brain uses hierarchical organization to process information from sensory inputs to higher order cognitive functions. Maybe mirroring that structure in AI architectures could lead to more robust reasoning.
Hierarchical organization, that's essentially what deep neural networks are doing, right? They're learning features at different levels of abstraction. The early layers might detect edges and corners, and the later layers combine those features into more complex objects. It's a bottom-up process, but it's still a hierarchy.
But it's a shallow hierarchy, in a sense. It's not a true symbolic hierarchy. It's not representing explicit knowledge and rules. It's just learning correlations between features. And that's why it struggles with things like logical deduction and common sense reasoning. You need a system that can manipulate symbols and apply rules to those symbols.
And I think that symbolic manipulation needs to be grounded in some kind of spatiotemporal framework. The symbols need to represent things that exist in space and time, and the rules need to govern how those things interact. Otherwise, it's just abstract symbol manipulation, divorced from the real world.
Okay, so let's get concrete. Sarah, what would a neuro-symbolic approach to reasoning actually look like in practice? Can you give us an example?
Sure. Imagine you want to build an AI that can reason about simple block stacking tasks. A purely deep learning approach might try to learn to predict the stability of a stack based on images of the blocks. But a neurosymbolic approach would explicitly represent the blocks as symbols, with properties like shape, size, and weight. It would also have rules about how those properties affect stability. For example, a stack is unstable if a block is wider at the top than at the bottom. The neural network part of the system could be used to learn to identify the blocks in an image and infer their properties, and the symbolic part would use those properties and the rules to reason about stability. This way, you're combining the pattern recognition abilities of neural networks with the logical reasoning abilities of symbolic systems.
That sounds complicated, and it feels like you're hand coding a lot of the knowledge. Isn't the whole point of deep learning that it can learn these things automatically from data?
But that's the trade-off. Yes, you have to put in more effort upfront to encode the knowledge and the rules. But in the long run, it's more efficient, more generalizable, and more transparent. You know why the system is making the decisions it's making, and you can easily modify the rules or add new knowledge without having to retrain the entire model.
And that's where I think the spatiotemporal aspect comes back in. Those symbols representing the blocks aren't just abstract entities. They have a location, an orientation, a relationship to other blocks in space. The rules about stability aren't just arbitrary logical statements. They're grounded in the physics of the real world.
So, Donald, how would you incorporate that spatiotemporal reasoning into a neurosymbolic system? What kind of representations and algorithms would you use?
I've been thinking a lot about different coordinate systems and how we translate between them. Imagine you have a robot arm that's trying to grasp a block. The robot's perception system might give you the block's location in pixel coordinates. But the robot's control system needs that location in joint angles. So, you need to translate between those two coordinate systems. And that translation involves understanding the geometry of the robot arm, the perspective of the camera, and the physical constraints of the environment. I think a good reasoning system needs to be able to do those kinds of translations smoothly and efficiently. Maybe using something like geometric algebra or tensor calculus to represent the relationships.
That's pretty abstract. Are there any existing AI systems that are doing anything like that?
Not that I'm aware of, at least not in a really general way. There are some robotic systems that use coordinate transformations for specific tasks, but they're usually hand-engineered for that particular task. I'm talking about a more general framework for representing and manipulating spatiotemporal information.
The issue becomes one of complexity at that point, I think. There is an inherent elegance in the simplicity of the logic that is used in symbolic reasoning, and that gets destroyed as you incorporate more complex spatial elements. How do you account for changes in perspective, environmental factors, the inherent messiness of the real world, and still have that reasoning be logically sound?
That's a key question, and I think that's where neuroscience can offer some insights. The brain is incredibly good at dealing with noisy and incomplete data, and it does so in a way that's both robust and efficient. I'm particularly interested in how the brain uses predictive coding to anticipate sensory input and resolve discrepancies between predictions and actual observations. Maybe we can incorporate similar mechanisms into AI systems to make them more robust to uncertainty and noise.
Predictive coding, that sounds a lot like the attention mechanisms in transformers. They're essentially predicting what the next word or token will be based on the previous context. Isn't that a form of predictive coding?
In a very superficial sense, yes. But the attention mechanisms in transformers are just learning statistical correlations. They're not really building a model of the world and using that model to make predictions. They're just learning to associate patterns in the data. It's still just brute force pattern matching.
And it's not grounded in space and time. The attention mechanisms are operating on abstract tokens, not on representations of things that exist in the world. They don't know where those tokens are located or how they're moving. They're just shuffling symbols around.
So let's bring it back to the idea of analyzing, predicting, and controlling reasoning models. What are the key challenges we need to overcome to achieve that goal? Otto, from your perspective, what are the biggest hurdles?
I think the biggest challenge is understanding the emergent properties of these large, complex models. We can analyze the individual components, the neurons, the weights, the activation functions, But it's hard to see how those components give rise to the higher level behaviors that we're interested in, like reasoning, planning, and creativity. It's like trying to understand how a flock of birds moves by studying the individual feathers. You need to look at the interactions between the birds, the rules that govern their behavior, and the environment they're operating in. I think we need better tools and techniques for analyzing those emergent properties.
I think the biggest challenge is bridging the gap between neural networks and symbolic systems. We need to find a way to combine the strengths of both approaches without sacrificing the interpretability and generalizability of the resulting system. And I think that requires a fundamental shift in how we think about AI. We need to move away from the idea that more data and more compute will automatically lead to intelligence, and towards a more principled and structured approach that explicitly represents knowledge and reasoning processes.
I think the biggest challenge is figuring out how to represent and manipulate spatiotemporal information in a way that's both efficient and generalizable. We need a framework that can handle different coordinate systems, different levels of abstraction, and different types of relationships. And I think that requires a new kind of algorithm, one that's fundamentally different from the algorithms that are used in current deep learning systems. I think it needs to be built from the ground up with spatiotemporal reasoning in mind.
And from my perspective, drawing from neuroscience, the biggest challenge is understanding how the brain achieves this kind of reasoning with such limited resources. We need to reverse engineer the brain's algorithms for learning, representation, and inference, and then translate those algorithms into AI systems. That requires a multidisciplinary approach, combining neuroscience, computer science, mathematics, and engineering. It's a long and difficult road, but I think it's the only way to achieve true AI.
So given those challenges, what are some specific research directions that you think are promising? Where should researchers be focusing their efforts?
I think we need more research on the neural correlates of reasoning in the brain. We need to use advanced neuroimaging techniques to map the specific brain circuits that are involved in different types of reasoning, like causal reasoning, hypothetical reasoning, and analogical reasoning. And we need to develop computational models of those circuits to understand how they work. We could also investigate synaptic plasticity and long-term potentiation, incorporating those findings into reinforcement learning algorithms to create more adaptive and robust models. That is a perfect application for neuroscience.
I think we need to continue scaling up deep learning models and training them on massive data sets. We need to see how far we can push the limits of this approach. And we need to develop better metrics for evaluating the reasoning abilities of these models. We need to go beyond simple accuracy on specific tasks and try to measure the process of reasoning, not just the outcome. I'm also really interested in exploring different architectures for deep learning models. Maybe we can find new architectures that are better suited for reasoning than the ones we're currently using.
I think we need to focus on developing more principled and structured approaches to AI. We need to explore different ways of combining neural networks with symbolic systems, and we need to develop new algorithms for representing and manipulating knowledge. I'm particularly interested in exploring different types of knowledge representation, like ontologies, knowledge graphs, and rule-based systems. Maybe we can develop a hybrid approach that combines the strengths of all of these different techniques.
I think we need to develop a new kind of algorithm for spatiotemporal reasoning. I'm not sure what that algorithm will look like, but I think it needs to be able to handle different coordinate systems, different levels of abstraction, and different types of relationships. And I think it needs to be grounded in the physics of the real world. I'm particularly interested in exploring different mathematical frameworks for representing space and time, like geometric algebra, tensor calculus, and differential geometry. Maybe we can find a framework that's well suited for reasoning about the world.
Those are all great directions, and I think it's clear that there's no single silver bullet. We need a diverse range of approaches to tackle this problem, and we need to be open to new ideas and new perspectives, because ultimately, understanding how a reasoning model thinks is not just about building better AI. It's also about understanding ourselves.
Exactly. It's a journey of discovery, and we're just at the beginning.
And hopefully a journey that leads to a more intelligent and more beneficial future.
Agreed. A future where we can finally build machines that truly understand the world around them.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We hope you found this discussion thought-provoking, and we encourage you to continue exploring these fascinating topics on your own. Until next time.